All right, today, first thing is voting on tests. So, let's take care of that right now. And remember, it doesn't matter, projector's on. Doesn't matter what day we do it to me, but I think Monday is best for you. Yeah, thank you.
Would it maybe help if we voted for the weeks separately so that half people's votes aren't going to nothing?
What's that?
Like if we voted for which week and then we voted for which day of the week?
It doesn't matter to me. All right, why don't we do it this way? Just show of hands here. How many want the test before spring break? Raise your hands. All right, you count. You don't want to ask this. 2, 4,
3, 5, 8, 9, 10, 11, 12, 13, 14, 15, 16.
What about more than that? Wait, put your hands up. I'll count. Hold them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18? Is that all? All right, after spring break. All right, hold them up. Just one hand. You can only hold once. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I think we've established that, unless you want to recount. All right, look, do me a favor. After spring break, can you give me the dates? First, give me the day of the week, and then the actual date. Anybody?
Wednesday.
What?
Wednesday.
This is after spring break. Wednesday, Monday, Friday after spring break.
That's 18, 20, 22.
18, 20, what is it?
22.
I'm sorry. Did you say another one over here or not? All right, this is smart. The week after spring break seems reasonable. All right, now, I'm just going to ask this. Raise one hand, we're going to vote on these. The top two will have a runoff. One hand, you count with me, all right? All right. If you want it Monday, one hand up. Just hold it there and get a count. I got 2, 4, 6, 7. All right. Wednesday, one hand. Hold them up. Oh boy. Forget it. It's not even worth counting. We got more than 2/3 easy. All right. It'll be Wednesday. All right. All right. So on Wednesday, this is test. And this is after spring break. Understand, everyone? Write it down. Now look, I'm fine with any day. I'm just leveling with you. It's better you choose. You can argue among yourselves. Because I don't really care. I don't. I'm going to have to grade it no matter what I do, and make, or somebody's going to grade it, but I'm going to have to make it. All right, now today, before I start into the lecture, I haven't got any real questions about the DTFT. I gave you, there was 1 or 2 problems I gave you on DTFT, right? You looked through it. Did you have any questions about the homework assigned or about the answers? Remember, you're going to see this, and it's very, very important you understand DTFT. This is the discrete time Fourier transform. The big difference, it's a sum, not an integral, but it still has an infinite number of terms, right? We're working our way in the direction. Anything at all? How many tried that homework, at least looked at it? Nobody. Wow, 1, 2. Okay, 2.5. Back there, 3.5. All right, I like this. I don't know. I knew it was there. All right, now I'm going to show you some things about this because we're going to use something that's akin to duality that'll help you immensely. Now, our book does not spend any time showing you some tricks, so I'm going to have to show you the tricks up here, and they're important. First, I want to finish the DTFT of the pulse. Remember, we did the DTFT of the impulse, of the shifted impulse, right? We did that of the decaying exponential. You all remember that class? There's one more we have to get before we get into the properties, and that's this pulse function that I showed you last time. If I call it P of 2Q of n, in the book he calls this a rect function, rect of really n over capital N. Now you have to know what this looks like. This has an odd number of terms. The n indicates the number of terms you go either above or below 0. Follow me? So if this is n terms, you're going to go 1, 2, 3, and then n terms here, and then 1, 2, 3, minus n terms here, but you have 0 here, and at that point, all these values are going to be 1, if you follow me on this. All the values are 1. Think of it that way. Lousy, but 1 here. This would be n equal 1, 2, 3, minus 1, minus 1, minus 2, minus 3, and so forth. So basically what it is a it's a pulse function, right? Only now at discrete values. Symmetric about the origin. You all see that, class? Now we're going to get the DTFT of this. This is a very important one. It's going to look like a sinc function, but it's not a sinc function. So when we do this DTFT of it, we know the definition of the DTFT of this pulse would be, and I'll call it this, x of omega would be a summation. Remember, the summation normally goes from n equals minus infinity to infinity of the actual function. I'm going to put it in here this one time. I'll put it in rect here of small n over n times e to the minus j n omega. Now this is important. Trust me on this one. You're going to get a lot more formulas coming at you. Work the problems when I give you, or it will not be imprinted on your brain. Very likely you'll have a terrible time recalling things and you'll have a lot of confusion. And that causes a lot of trouble on the final. What I'm trying to do is warn you in advance for what I see. On the final exam, I have the biggest discrepancy in grades. I get hundreds and I get almost 0, like 2 5 points kind of stuff. So I get a tremendous span. I get a lot of failures and a lot of A's kind of deal. So just remember that. And the more you spend time now on this stuff, the more it's going to be burned in your brain. You're not going to forget it. Just remember what I tell you. So anyway, that's the formal definition, right? Now, this rect of t is just the value of 1 between minus n and plus n, right? So how are we going to deal with that? Ask yourself, how would you deal with it if you want to calculate? Anyone? What do we do? Well, we're going to erase that for starters because that's 1, right? But where is it 1 from?
From minus n to plus n.
Right, and now we just change the limits. Remember, that's the only thing we do for this one. All right, understand, class? That's it. Now, in that sum, remember last time I showed you that if we have a sum, and this one you have to know, from Q1 to Q2 of any, well, for this function of a to the n is what I used, I think, or something like that. What I really get is what? A to the Q1 minus a to the Q2 plus 1 over 1 minus a. Do y'all remember that? This is a standard geometric series. You have to know that formula. You don't have to. Yes, sir. Did you ever have it?
I did.
Okay.
I just never did that. I'm sorry.
Well, here's the deal. This thing has a value of 1 only. I should do this. See, these are all zeros out here. And these are all zeros after here, right? So the only values that are not 0 are between minus n and plus n, right? Well, the definition says here that it's the rect, it's any function, but it's the rect function, in this case, times e to the minus j and omega naught. That is the definition of the DFT, right? Well, since the rect function has a value of 1 between minus n and n, that's all we need, right? Because it's 0 outside there. 0 times anything will be 0. Okay, that's it. Everybody got that? There are no dumb questions, so don't worry about it. Now, here, that we can use that formula. You'll need to know that formula. I can't say that enough. I know people will come up to me, well, it's at least an obvious possibility, and say, I don't remember that formula. And I'll say, well, you should. Because you should use this thing over and over again. It should be something that you're going to use 5 or 6 times every time you do DTFT problems. Do you understand that, class? You'll be using it. Now, when I take a look at this, I need to fit that form. So how do I fit that form? I need something to the power n, right?
Yes.
Any takers on it?
So
Go ahead.
A equals e to minus j omega.
You're right. So I'm going to have e to the minus j omega to the n power. Does everybody see that? Show of hands here. Make sure you can think through stuff like that. You all see that? Now, what is that going to be? Well, now that's like a, isn't it? So I take that power, e to the minus j omega times minus n, right? Correct, class? That becomes plus, minus e to the minus j, right? Omega times what? N plus 1, correct, class? Over 1 minus e to the minus j omega. Do you all agree with me here? Please watch this. Make sure you see it. Show of hands here, how many see that? Go ahead, check me, be suspicious. Always suspect I made a mistake. I probably do sometimes, so catch me when I do it. Y'all agree with that? Give me a show of hands, how many see this? Now you're gonna have to do these kind of things. That's the reason I'm spending time on this little proof. All right, now I want to make this into something that's reasonable. Something like a sine. So how am I going to do that? Well, first I'm going to go downstairs so you see this one pretty easy. If I take 1 minus e to the minus j omega, does everybody agree I can factor out an e to the minus j omega over 2 as a phase shift? Get used to this. This is one of the tricks you see all the time. Then I'm left with e to the plus j omega over 2 here, and it's minus e to the minus j omega over 2 here. Is it not, class?
Where, so did n become omega?
This is n
Oh, sorry.
omega, this is omega times n plus
Oh,
1.
okay.
The formula here that I had, this is whatever this limit is plus 1, but remember a is e to the j omega,
Oh, okay.
or e to the minus j omega part. Follow me, class? Show of hands here, got this? Just work with me on this. All right, work with me. Now y'all see this right here, what I did? I took the denominator on purpose and just broke it out to show you how I'm factoring. How many see this right here? What am I going to do with this term? How many see that's 2j times the sine of the argument? Right? And don't ever forget those Euler identities. Sine of anything is equal to e to the j theta minus e to the minus j theta over 2j. Do you all agree with me? This you must know, like the back of your hand. So if I multiply both sides by 2j, right, I get that. I look here, my theta is omega over 2, correct? But I have the 2j here. So downstairs, or in the denominator, I will put this is equal to 2j times the phase shift, e to the minus j, omega over 2, times the sine of omega over 2. Agreed, everyone? What?
Which there? Did you just like move the denominator to the left side?
I just took this as the denominator, right? The denominator is here, correct? Is here. I'm going to put what's up here in a second. All right, do y'all see what I did here? Show hands here if you see it. All right? So what I'm trying to do is just show you how this can be turned into a sine times 2j times the phase shift. Yes, sir.
Can you re-explain how you got the negative e?
All right, what happens if I multiply this times this? Just tell me. I have e to the minus something times e to the plus something, right? Don't you add exponents? E to the minus something plus something is 0, is 1. Understand, class? These are good questions. It's not apparent to some people. Trust me on this one, I know this. All right, does everybody follow me how I got a 1, how I factored an e to the minus j omega over 2 out of a 1, and I'm left with e to the plus j omega over 2? Guys, make sure you see this. This stuff will come at you all the time. In your upper level courses, they're going to be doing stuff like this all the time. A lot of heavier tricks than this, things that will really make your eyes crossed. All right, now I have that. I want to turn this into a sign. Think about this carefully. Now that's a plus, that's a minus, that looks good so far, right? I got a minus sign there, we're doing good. What do I need to factor out of this thing? Well, if I factored e to the j omega n over 2 out, right? I'd be left with an e to the j omega n over 2 here, right? But here, that 1's a problem, isn't it? All right, what do we do? Well, let's just think about this. And if I take e to the j omega, or n omega, I think you know what you're doing. Yeah, I heard it right. I think I heard it right. If I factor out e to the j, and now it's going to be omega n right there, or e to the mic. No, let me see. Yeah. Plus 1/2 out. Hold it. Let me do it right. E to the j times n, or times omega, pardon me, times n plus 1/2 times omega. If I factor that out of there, then I'm left with sorry, I got that wrong. That should be e to the j, and that should be n over 2, n plus 1 over 2 times omega, pardon me. N plus 1 over 2 times omega out in front. Then I'm left with e to the j and let's see, does that work? Oh, this is gonna have to be a minus there. Pardon me. I'm not sure if that's gonna get it.
You can move
And this is gonna be sine of n plus 1. Go ahead, what were you saying?
move the one in the denominator to the numerator, the e j
Hold on.
omega over 2, and that will cause that'll
This
cause
one
the
here?
one to co-
Are you talking about that?
That'll cause the 1/2, the one in the
Actually, you're
second one
right about that.
become 1/2, and the first one to gain.
You're right. You're right about that. You're absolutely right. That's the easiest way to do this. E to the j omega over 2 here, and then it would be e to the j omega, and here, minus e to the minus j omega n plus 1 here. And then when you go through the multiplication, you do addition of these things. You're absolutely right about that. Thank you. You can just do it right here. I was trying to finagle that thing, but it's easier to see here, and that will be equal to e to the j, and this is going to be omega times n plus 1/2, and then it's minus e to the minus j, and it's going to be omega times n plus 1/2 here. That's absolutely right, and it's still everything's going to be over 2j right here, and then it's going to be times the sine of n psi over 2. You're right. Now, I needed to get it to this form for one reason. Now, this argument is the same thing as this argument, except for that minus sign, right? And now I know, thank you, by the way, that's going to be a sine of that argument, right, with 2j in front of it. Does everybody follow me on that? Show of hands, right? So I can say that this now, the top part will be equal to 2j times the sine here of, it's going to be omega times the quantity, well, let me do it the way the book does it. He has sine of n plus 1/2 times omega, right there, and it's divided by 2j times the sine of n psi over 2. And that is the transform of this. That is my x of omega. What do you see happening to the 2j's, guys?
Cancel.
They cancel. Now, I'm going to talk about this. This is right. And I can write that a little larger if you want to see it. X of omega, the transform, will be equal to the sine of quantity n plus 1/2 times omega over the sine of n plus, or I'm sorry, over the sine of n, there's no n there, pardon me, over the sine of psi over 2. I'm sorry about that. There is no n there. That was my fault. All right, does everybody see that?
What's
Please.
the theta in sine?
I couldn't hear you.
What is the theta in sine?
It's not theta, omega, pardon me. That should be omega over 2. All right, now that's what I wanted to drive at. When I get to this point, this is important. You see, it looks a little bit like a sinc waveform. We have a sine of something, but it's not divided by what?
By
It's not divided by n plus a half over omega, right? It's divided by this. Correct, class? What this is called, this looks like a sinc waveform, and I want to say one other thing. The sine of a small angle, like sine of x, if x is small, is approximately x. Do you agree with that? What you can actually see this looking like is a sinc waveform. I'm going to draw it up in the book here as several examples, but it's not a sinc. It does appear to be a sinc, and I'm going to show you some of the characteristics of this waveform. It's an important thing you see right here. So let me do it right here. When I take a look at this right here, which is the transform, right? It's a transform of my rect of small n over capital N function. That's that pulse function. What that looks like is something that has a height at 0. This is going to be values of omega here. And remember, it repeats itself every, this goes from minus pi to pi, it repeats itself every 2 pi. Correct, class? Now follow me. Right here, the height of this thing is going to be 2n plus 1. That's how large it gets. So the more terms in the actual, or the wider the pulse width, what you see happening is the greater the peak. And I want to just make sure you see one other thing too. This is important that you see the parallels. I'm going to leave this up, but I'm going to get rid of this stuff so you can see some parallels. It'll be important. The first parallel you're going to see has to do with the height. Remember, if I had a pulse waveform, p tau of t, which is the same thing as a rect of t right over tau, if that transformed into tau, right, tau times the sinc function of omega tau over 2, correct? Isn't that right? What's the magnitude of the sinc function? What's the maximum? Say when omega is 0. 1, right? But notice it's weighted by tau in front. So the sinc function itself, if we were to plot that versus omega, if we were to plot tau times the sinc of omega tau over 2 versus omega here, this would have a height of tau, and then we come down like this and so forth. You all follow me on this, class? Over here, this function starts at a height that's proportional, you might say, to the weighting function in front of omega, right? It's actually proportional to what? Twice that, isn't it? It's 2n plus 1, so it's twice this. Do you follow me on this, class? This is the height, 2n plus 1. And then it goes down, and where's the first 0 appear? Can you tell me? Well, this is a sine. Where does sine go to 0? At 0, at pi, right? It goes from sine, it goes 0, and then at pi, it's back to 0 again, isn't it?
Yeah.
Then at 2 pi, it's 0, correct? So the first 0 here would correspond to that argument, n plus 1/2 times omega. Omega here being equal to pi, or omega is equal to pi divided by n plus 1/2. And likewise this, so this would be pi over n plus 1/2. This 0 here would be minus pi over n plus 1/2. What you can see is the larger the value of the n, the narrower this becomes, and the higher, the taller it becomes. Y'all follow me in this class? What that corresponds is that the energy, or you could say that the most of the energy in the first lobe, if you power, if it's a repetitive signal, but energy, if it's a one-time pulse, is in the range from here, minus pi over n plus 1/2 to plus pi over n plus 1/2. Follow me? That's the one thing to remember. And remember what this is going to do. Here's what I should say too is, remember if n is fairly large, then this can be approximated as just omega over 2, right? And the thing about this is this function down here is changing very slowly compared to this function. So it means really you can basically just graph the top part of that, the sine of n plus a half times omega versus omega, and you pretty much have the sketch of the right function, the first low, to the first zero. If n is like 10 or more, for sure. Then it goes down, and it starts looking like a sine or sinc function. It looks very much like a sinc function. The book has a picture of this, I believe. You all see this right here? This is a real important one to understand. You see it all the time. Now next, the next thing I've got to do is talk about some properties before we actually get into some of the actual problems. Well, we'll use these properties all the time, but this is important. All right, now for the properties, they're almost identical to those of the Fourier transform, if you look at them. Can you tell me what page the properties are on in the book? This is for the DTFT. And I've got to show you a very important property. If you don't know it, don't worry. Anybody?
Oh, maybe 378?
Is it page 378, class?
Right, yeah, properties of the DTFT.
That's the one you want. Now, I want to mention it. I have a different book than you. This book's a little more complete with DTFT, but I'm going to show you something. We did the pulse, we did the delta function, we did a to the n u of n, correct, class? We got the DTFTs of these. You're going to have to know these. These are the ones you have to know. I'm going to do, I'm going to show you duality using the DTFT. And this is something that's so powerful. Remember, what did duality say back in the continuous time Fourier you made? It says if you had an x of t that you knew went to an x of capital omega, correct? If you had that information, then you could take this functional form, the large X of omega, replace the argument of omega with t here, then you could take the form of this argument and replace, first you'd have to put a 2 pi, and then you would replace the t with a minus omega, right? And then you would have the transform pair in the opposite direction. Does everybody understand that? Now that is extremely important, extremely powerful. If you think about what the definition is, first for the Fourier, then the inverse Fourier transform. For the Fourier transform, it says that x of small omega was equal to the integral from minus infinity to infinity of small x of t times e, right, to the minus j omega t dt. That's the definition of the it is the Fourier transform. It's really analysis. Then synthesis, or x of t, now synthesizing x of t, was 1 over 2 pi, the integral from minus infinity to infinity of capital X, I'm going to go ahead and make that capital X of omega, times e to the plus j omega d omega. And this here is actually synthesizing a signal, if you think about it. If we had a filter property in X of omega, then we would know what the impulse response is just by doing that. That's the way you can think of it. All right, now that's the Fourier transform. For the discrete time Fourier transform, the X of capital omega is equal to the summation, right? N equals minus infinity to infinity of x of n times e to the minus j small n of omega. And x of n here is equal to 1 over 2 pi, the integral from minus pi to pi of capital X of omega times e to the minus or plus j n omega, right? D omega. Does everybody follow me on this, class? I want you to watch this. Now focus down here on this, right here. and this right here. Because here's where it really becomes important that you focus. Now, if you look at these two things, they look very similar. They have a 1 over 2 pi in front. They have an argument, that's a capital omega, this is a small omega. In some books that discuss the actual really Fourier transform and discrete time Fourier transform, they'll use a small omega here too. All right? They just won't even make it, they will not make it distinguish it by a symbol change, and it doesn't have to be. Now here, what do you see? You got a small omega, a large omega, a t and n, right? Identical as far as the variables. Here you see a capital omega, they're a small omega. They're identical almost everywhere. I mean, there's a variable symbol change, nt, right, or tn, whatever you want, and capital omega, small omega, but otherwise they're the same except for one thing, the limits. You see here the limits are from minus to plus infinity. You all see that? Now here's the real neat thing. If you know a Fourier transform pair in the continuous time domain, listen carefully, but the x of omega is only non-zero between minus pi and pi. All right, it only has a non-zero value between minus pi and pi. Then this limit becomes this limit's range. Do you all follow me on that? I'm going to do you an example. How many see what I'm saying? Then the transforms would be identical. You would take the x of t, and you would simply take t and make it n. I'm going to make this real for you, all right? Everybody hear me on this? Because of the similarities, if you could find an x of small omega, right, between the range of minus pi and pi, that is exactly the same as this x of big omega, and you know what x of t is, then you can just take the x of t, take the t and replace it by n. I'm going to give you the actual problem I'm talking about, because this is so important. So now, let me do it. I'm going to erase this stuff. I'll do it on this side of the board. And it gets good. All right. Anybody want to take a guess which one I'm talking about? This has to do with the inverse dTft. Well, there's a couple. I'm going to start with the most obvious. Suppose I gave you this. X of omega, this is going to be x of capital omega, here looks like this. From minus pi over 2 to pi over 2 with a height of 1. That's in the omega domain. Do y'all follow me? I want to know what x of t is. What caused this? What is, or x of n, pardon me. What is x of n that caused that? Now, what did I tell you? First of all, is this only, I mean, this is between minus pi and pi for sure, because we know it repeats itself, correct, class? But y'all see that we have something here. Now, if we go to the continuous time domain, let me drop right under here. This is the question you have to ask yourself. If I go from minus pi over 2 to pi over 2, and instead of making it capital omega, make it omega, and make this x of omega right here, do you know the inverse transform of that? Class? How many do? How many realize that you can use duality to get that from the actual transform of a pulse, right? Now we've done that twice at least. I'm going to do it a third time. And from here on, you have to know this one like the back of your hands. I'm going to do it right here. Now just work with me if you don't remember it, because you're going to see this stuff and it's going to be, you're going to get tested on it. Using duality, do you all agree that if I have a pulse function from minus tau over 2 to tau over 2, height of 1, that's my pulse function, p tau of t, that this transforms into the frequency domain as simply what? Tau, right, times the sinc of omega tau over 2. Do you agree with me, everybody? Now, using duality, I can take that function, right, and I can say that's tau, and then it's going to be times the sinc of not omega, but t tau over 2. Do you all follow me what I've done there? I'm using duality. So I replace omega with t, correct? Now I come over here and I say I take this is in the continuous time domain, and I put a 2 pi in front of that, right? And then I take it, make it p tau of minus omega, correct, class? I'm going to go ahead and divide through by the 2 pi. How many see what I'm doing here? Are you with me? You got to see this stuff. It's going to be something you're going to be tested on. Now I'm going to divide by 2 pi for a reason. And the reason is I want a coefficient of 1 over here. Got one more thing to do. Can anybody tell me what to do with that minus omega? Can we make it a positive omega because it is an even function? How many see that? Sure we can. So get rid of it. Now, you'll notice my actual function that I'm looking for, the actual tau is pi, isn't it, class? Y'all see that? So the width is pi, so make this pi. And if that's pi, this is 1/2. And if that's pi, that's it, correct? Now this is the one I wanted. This is the one I now have, correct? In continuous time. So what did I say? You would take the x of t, or this, and simply replace t with n. Got that, class? That's how easy it is. You don't have to do an inverse integration. To get x of n here, I take this x of t that I had, which is 1/2 times the sinc of t pi over 2, and now replace the t with simply n, or it's 1/2 times the sinc of n pi over 2. That would be x of n, and this would be the frequency domain response. Now I've got to make this comment. Are you ready for it? I want you to listen. If I could generate this waveform, and it's theoretically possible, then this is the actual frequency response I would see on an or on a spectral analyzer. Do you all follow me on that, class? Show of hands, somebody see that. However, if this was a filter response, if this was h of capital omega, now that's my filter response. And I plugged in an h of n, an impulse response, right, to this. Well, this is the output of the filter, isn't it? If the impulse goes in, this is my output. And it looks like this, doesn't it? Is that possible? If yes or no? If I have a perfect filter in discrete time and I send in an impulse, isn't there an output occurring before n equals 0? Remember what this filter property looks like. I'm saying to you, if I have a filter here, right, and I put a delta n in to this thing, my output is h of n. That is in the discrete time domain. Here, if I take a look at the spectrum of that, or the transform, that's h of omega, right? Well, that means this is actually got a filter property of h of omega, correct, class? If I put an impulse into this thing, this is my h of n. This would be my h of n. Do you all see that the impulse occurred at n equals 0? That's the only non-zero value. But this has values that are non-zero for what? Negative time. That's impossible. All right? That's a non-causal filter, and that's why this is something you can't really have in real-time filtering. You can't have anything that anticipates what's going to happen at 0. But where you can use this if you have a data record. If you have a data record of everything from the beginning to the end, like over 365 days, think of it that way, then you can apply a perfect filter. And that's the only time, or I call it an ideal filter. Understand, class? This is called, yes, sir. Did you have a question? Okay. Now, that's one. Let me ask you the next one, which is obvious. And these are good ones. Anybody want to anticipate the next one I'm going to ask for the inverse of? We'll do the other properties in a second. Huh?
Probably a triangle pulse.
Very good. You are very good. Sure. What if I gave you this as the filter response? 1, and make this minus or plus pi over 2, and this minus pi over 2, height of 1, This is capital omega. And now I want x of n. How are you going to get that? Very, very common for me to do something like this. Remember, I'm going to take combinations of both of them. Anybody? Well, how many know what the how many know what the inverse of the triangle function is? Let me ask you this. If I go to the time domain and I put a triangle function in, how many know what the output is in the frequency domain? A couple of you do. You have to know this one. I mean, these are things you're going to have to know because you're going to be seeing them all the time. If you have a triangle in time domain of width t, right? Triangle function, this goes to what? Tau over 2 times the sinc squared of omega tau over 4. Do you all remember doing that? Now remember, that's going from time to frequency. Using duality, we want this in a frequency domain, don't we, class? But first, we'll take this and bring it over here. And now I have tau over 2 times sinc squared of t times tau over 4 here. What do I do with this over here, class, using duality?
The minus over.
First. Don't forget the 2 pi always. 2 pi, and then it's going to be times the triangle function of width tau of technically minus omega. But what do we know? Is a triangle an even function?
Yes.
Yes, so we can make it plus omega, right? My next step that I like doing is to divide by 2 pi. So that means this is 4 pi. Y'all all agree with me? You can see it now like that. A lot of you can. I wanted the inverse of this, right? This is my x of capital omega, right? What's going to happen? Well, first of all, this would have a width of what? Just tell me. Look over there. What's the width of that? You all see it's pi, everybody? Sure, pi. If tau is pi, right? Isn't this 1/4? And we just put pi in here, right? Finally, do you all agree that that and this, that over there, the x of small omega, or the triangle function of omega there gives me this in the time domain. It only has non-zero values between minus pi and pi, correct? Now we can take this t and make it an n, and we can make this omega capital omega. Do you follow me in this class? And now I have the inverse transform of this, or the impulse response if that's a filter property. Follow me, class? And again, is this one allowable in real time or not? Is it a causal response or non-causal? Non-causal because it has values, right, that are non-zero for n less than 0, and an impulse would come at n equals 0. Do you follow me on this? And turn on. All right, good. Now I've got those two things. That's the hard property. Now, by the way, we're not getting a quiz, but you have a project to grade, so don't leave. I got it up here for you. Next thing, no, not you, him. It's your project, by the way. All right, now let me go through some of the other properties, because in the sheet on properties, these are ones I can prove to you, but the thing about it is it's not important about how, I could go through the proof, but they are identical to the Fourier transform. First of all, if I have x of n, write these down, these are important. The book should have these, and guys, if you have your books, leave them open to the property sheet and tell me if the book has this property. Cosine of omega naught times n. Omega naught is a frequency, like small omega naught before. And this simply goes to, anyone want to take a guess? Identical to the other one, x 1/2 times x of omega plus omega naught plus x of omega minus omega naught. We're going to use that property. Means if you know the transform pair x of n goes to x of omega, the only thing you do is take that argument omega and offset it by plus omega naught, omega plus omega naught, and by omega minus omega naught, and just stick those values, that formula in there. You all see this, class? It's very straightforward. Next is x of n. Does he have this one in the book, by the way? Or not? add that one. He probably has the exponential.
Yeah, he's got that.
All right, but that's the exponential is not enough. Write that down. Now, if he has x of n here times the sine of omega naught n, any takers on what that's going to be? Almost automatically.
With a
J
minus.
over 2, right? J over 2 of x of, say it, plus omega naught minus x of omega minus omega naught. Very good. Same as the Fourier transform, correct, class? These are good properties. So those two, and those are modulation properties. They're important. Next, I'm looking at the ones that are most important. He does do the exponential. I'll just show you this. He should have this down. If he has x of n here times e to the j, and he'll have omega naught n, that's going to be simply x of, and this would be omega minus omega naught. He should have that one. Does he, class?
Yes.
Take a look. He may not use omega naught there, but it should.
Yeah, he is.
Which property is that, by the way?
Frequency shift.
I mean, what number?
Number
3?
I have first edition.
If you look in there, this is a you can actually create the sine and cosine from that one if you want. That's an important one. I did the pulse already. All right, now one other thing too. What if you have 1 here? Any guesses on what happens over here? Think about, remember we did DC before? How did we find out what it looked like in the frequency domain? We used duality, right? Right? Sure. Do you remember? Come on. Now think about this. I'm trying to show you a way to think about these things in terms of the continuous time domain. If you had delta t, right? That went to what? I should say 1, pardon me. Yeah, all right, we'll do it that way. Delta t goes to 1, and therefore 1 goes to 2 pi times delta of minus omega, right? But does it matter if it's minus or plus? No, it's plus omega, correct, class? Now that's a DC term. 1 is indicating nothing's changing in time. It's just like a DC voltage. And you'll notice in the spectral domain, everything occurs at omega 0. That should make sense. There is no other frequency component. Now, when you have a 1 here, there's one thing different. I'm not going to prove this right now. But there's going to be the 2 pi delta of omega, right? It's definitely going to be that. But it's more than that. It's 2 pi delta of omega. But it's going to repeat itself every 2 pi, correct, class? So what normally is done here is they're going to say this is really going to be a sum of 2 pi delta of omega, all right? And it's going to have minus or plus, it doesn't matter, n, really 2 pi n. That's how your book should have this. And they're going to have n goes from minus infinity to infinity. Do you all see that in your books, class? You should have 1 goes to 2 pi times a delta function of omega plus 2 pi n. Do you see it?
Yeah.
Which one? Which property? Or which transform pair? Pardon me.
That'd be 2.
Is it 2?
Yeah.
Number 2. Remember that one. That's really important. You get it through duality. You remember it repeats itself every 2 pi. That's how come that's there. Understand, class? That's the one reason. Usually you only care from minus pi to pi. A couple more things about the DTFT. And I want to get to some problems, but with convolution, this is the other thing. Just make sure you know that if you have x of n convolved with h of n, that's going to go to x of capital omega times h of capital omega. It's the same thing. We can prove that if you want. It's the same thing as in the continuous time domain. Understand, class? That's wonderful because that eliminates convolution, if you can appreciate that. All right, I'm just trying to hit the properties that are valuable. You remember before you had t, right? T times x of t, and that went to what? J times d omega of x of omega. Do you all remember that, class? How many do? All right, that's a you got to know that one. All right, well here, if you have n times x of n, this is a property, that's going to go to j times the derivative with respect to capital omega of x of omega. Does he have that property down, clearly stated? It's multiplication by n?
Is that n times
It'd be property 4.
Property 4, I'm just trying to show you the ones. We proved this in continuous time. That's partially the reason I'm not spending a lot of time proving it in discrete time. I'm about out of time here. I didn't get a chance to do some of the problems, but I've showed you a couple of the inverses, right? And I gave you the problems and the solutions. Now, you haven't worked them, but you need to. On Monday, I'm going to take off on this What I'm going to tell you is, if you're smart, you're going to do this homework. This is going to be something that's going to really start becoming a little more complicated. There's more things going on. I'm going to give you some homework with solutions. Yes, sir.
Is this the last of the material that's going to go in the test?
Well, it's the day before the exam. What you do is Wednesday is the last bit of material, but technically, I mean, that's technically where it would be. But frankly speaking, right through the next couple of days, this we're going to just flesh out. So this material is what we're going to be discussing. Yes. Okay. All right, class. Enjoy the weekend.